Hi everyone, welcome to the session. In this session, we'll be discussing uh, some important uh, formulas and the frequently asked questions in GATE examination. Okay, so coming to electrical machines, I'm going to take up in four parts. All these four parts will be covered in this session itself. Very quickly, I'll be covering. So the first part is going to be transformer, and the second part is going to be induction machine, and the third part is going to be DC machine, and the fourth part is going to be synchronous machine. Okay, so let us see some important formulas and some questions which were asked in previous GATE examination. Okay, if you look at this, the topic is construction and operation, and in the construction we'll be discussing about core and windings, and in the operation we'll be discussing about no load operation and full load or any load operation. And definitely we'll be discussing about EMF equation, and the EMF equation is given as 4.44 into F into phi into N. So from this equation, you can say that the EMF per turn on both the sides will be equal. Now here, B maximum into net area of cross section is replaced instead of phi. And from this equation only, we can write the B maximum is directly proportional to EMF and inversely proportional to frequency. Otherwise, the flux density is directly proportional to voltage, applied voltage, and inversely proportional to frequency. This is very, very important formula. And during load operation, during no load, it will take no load current. And during load, it will take one more current on the source side, that is I1 dash. I1 dash value is transformation times the load component of current. Okay. So from the MMF balance theory, from MMF balance equation, whatever the magnetomotive force produced on the secondary will be compensated by the magnetomotive force produced on the primary. So I can say that N2I2 is equals to N1 I1 dash. It's actually not I1, it is actually I1 dash, which is going to compensate the magnetomotive force or the flux produced at the secondary. Now from this one only, we can take up here N2 by N1 is equals to I1 dash by I2. And we know N2 by N1 can be written as E2 by E1 from this EMF per turn equation. So therefore, on the whole, the supply current is going to be no load current plus load component of current. Remember, load component of current on the source side is transformation times the load current. All right. So this is a vector sum. It is not an arithmetic sum. And if you are going to add vector sum, you need to consider the power factor angles also, or the current at which it is lagging or leading with respect to voltage, you need to consider. Generally, the phi naught is going to be lagging with respect to voltage, because generally, the core nature is inductive nature, and hence it is going to be lagging. And coming to the phi 2, it can be leading or lagging based on the load. If it is capacitive load, it will be plus phi 2. If it is inductive load, it will be minus phi 2. Okay. Right. So that's what I have written here: no load power factor angle and load power factor angle. Let us have one question on this one. If you look at the question, this is asked in previous GATE examination. He has given a 3-winding transformer, and 3-winding transformer turns ratios are given as 4:2:1. And at winding 1, he has connected 400 volts at an angle 0 volts supply. And at winding 2, he has given 10 ohms resistance. At winding 3, he has given 2.5 ohms capacitive reactance. Now he's asking the supply current phasor is given by. So just now we have seen supply current phasor is nothing but no load current plus load component of current. Here, no load current is going to be absolutely 0, because the transformer is an ideal transformer. If it is an ideal transformer, losses are going to be 0. If losses are going to be 0, then I can write working component of current will be 0. Similarly, if it is an ideal transformer, the permeability is going to be infinity, and hence the magnetizing component of current drawn by the transformer core is absolutely 0. On the whole, the no load current is going to be 0. So here the primary phasor current is nothing but simply load component of current. What is the load component of current? It is K times I2 dash, or K times I2. We have two loads, so you'll be getting two components. Okay, if we have two loads, you'll be getting two components. So let me write here. So total I1 is equals to K times IR plus K times IC. Yes or no? On the source side, okay. What is IR? IR is the resistive nature current, and this current is going to be voltage divided by resistance. I know the resistance value as 10, but what is the voltage? I'm applying 400 volts on the source side. For 4 turns, if it is 400, now 2 turns, it will be 200. EMF per turn will be equal, na? So if it is 4 turns, 400 volts if it is bearing, and 2 turns it will be bearing, or it will be getting 200 volts. Similarly, on 1 turn, we will be getting 100 volts. So 200 divided by 10, it will be 20. So I can write now K is going to be transformation ratio N2 by N1. You will get it as 2 by 4 times 20. And similarly, K N1, N3 by N1, it comes out as 1 by 4 times IC. IC is going to be voltage divided by the reactance or the impedance. I can write it as 2.5. To say exactly, you have to write it as minus J 2.5. So you'll be getting it as plus J 40. So if I write IC as plus J 40, then I can write here it as 10 plus J 10. So this is the current which is drawn by the primary side, or the source is going to drive this much amount of current. So hence the option is 10 plus J 10. Okay. You can use MMF balance theory also. That is N1 I1 is equals to N2 times I2 plus N3 times I3. This is what K actually. K is nothing but what N2 by N1 only. Na? So this is what, if you bring this N1 onto this side, it will be divided by N1 divided by N1. The same formula here. Either you use this formula or you use this formula, you'll get both. You'll get the same answer in both ways. I hope it is clear for everyone. Moving on, the next important topic is equivalent circuit of the transformer. So when you transfer the secondary parameters onto the primary side, you will be having, it's like R1 will be there, and along with that, R2 dash will be there. Similarly, X1 will be there, and along with that, X2 dash is also there. Okay. So here, R2 dash is given as R2 by K square, X2 dash is given as X2 by K square. And on the whole, if you refer on to the primary side, maybe I can connect a load here by neglecting the no load branch component. You'll get like this. So the total resistance referred to the primary side is going to be R1 plus R2 dash. Total reactance referred to the primary side is going to be X1 plus X2 dash. The point you need to remember is this one, R2 by K square and X2 by K square, when you are transferring secondary parameters to primary side. Similarly, if you are transferring primary parameters to secondary side, then we'll be having here R2 and R1 dash, X2 and X1 dash. Okay. So here is my E2, and by the way, here you'll be having the load. Now R1 dash is K square times R1, and X1 dash is K square times X1. You need to remember. Similarly, the total resistance referred to the secondary side is R2 plus R1 dash, and total reactance referred to the secondary side is X2 plus X1 dash. Okay. Right. So based on this, sometimes they'll ask the question. And you see here, there is a simple question which is asked in the previous gate examination. He's assuming an ideal transformer and is asking Thevenin's equivalent voltage and impedance seen from the terminals X and Y. So this is the terminals X and Y, and you need to calculate Thevenin's voltage and Thevenin's impedance. Okay, let me check with the Thevenin's impedance first. So if you are trying to calculate Thevenin's impedance, what you need to do, you need to short the voltage sources. There's actually V of t. V of t is equals to sine omega t. And if you short it and send this primary parameters to the secondary side, so if you short it and send the primary winding parameters to the secondary side, If I make it as R, then it will be R dash. What is R dash? When you send primary parameters to secondary side, it will be K square times R. No? So this is my X and Y. What is K? The transformation ratio, you will get it as 2 by 1. So I'll be getting 2 square into 1. You'll get it as 4 ohms. So ZTH, the Thevenin's impedance, is equals to 4 ohms. Now, similarly, the Thevenin's voltage. Okay. As it is an ideal transformer, we do not have any load. So it's an open circuit. The current drawn by the transformer on the primary side is absolutely zero. Under no load current, the no load current is zero because it's an ideal transformer. And hence no voltage drop across this resistor. So whatever the voltage you are applying across these terminals, the same voltage is available across this winding. That is sine omega t volts. For one turn, if it is sine omega t volts, then for 2 turns, it will be 2 sine omega t volts. Now, the voltage induced or the voltage available across X and Y terminal is Vxy or Vth is equals to 2 sine omega t. So this is the voltage which is going to be available across X and Y. So in that way, we can take up. And the next important topic is testing of the transformer, where you can test the transformer on the core and on the windings. So the core test is called as open circuit test and the winding test is called as short circuit test. Now, if you want to test the core, you need to allow the flux density as a rated flux density, right? Now, at that point, you can find out the reasons behind the core losses. That is R0 and X0. These are magnetizing branch parameters. And if the magnetic flux density is going to be constant, you can write the hysteresis loss is directly proportional to frequency. Of course, let me repeat it once again. If the transformer is designed, once the transformer is designed, the volume of the core and the thickness of laminations here is going to be constant. So I can write V maximum power X into F, and eddy current losses can be written as V maximum square into F square. Now the point is here, they'll ask you the question like this. If the transformer is designed for rated voltage and rated frequency, and the transformer is again operated at other than the rated voltage, other than the rated frequency, but the ratio is constant. Voltage to frequency ratio is constant. For example, if the transformer is rated at 200 volts and 50 hertz, now if it is operating at 100 volts and 25 hertz, you check the voltage to frequency ratio. The voltage to frequency ratio is going to be here, it's 4. And now see here, the voltage to frequency ratio, still it is 4. So the flux density is not changing. So flux density is constant. If the flux density is constant, I can write hysteresis and eddy current losses as proportional to frequency and proportional to frequency square. And from this one, you can take up Wi is equals to A times F plus B times F square. And this is where we use to separate the hysteresis and eddy current losses. We use this formula to separate hysteresis and eddy current losses. Sorry, to separate iron losses into hysteresis and eddy current losses. Now, if the voltage to frequency ratio is not constant, then the flux density is not constant. Then you need to consider this flux density. So if you consider the flux density, yeah, you'll get it. So B in place of B maximum power X, I have written V by F whole power 1.6 into F. So here F power 1.6 into F. No? So if you bring F to the denominator, you'll be getting it as F power 1.6 minus 1. You'll get F power 0.6. Here X value is 1.6 is taken for gate examination, and this is hysteresis coefficient. And coming to the eddy current losses, when you substitute V by F whole square into F square gets cancelled, and it will be ended up with P square. Similarly, if you can maintain the voltage as constant and the frequency is reduced, that means what? If the transformer is designed for 200 by 50, I'm applying 200, but frequency is reduced. Then flux density is not constant. So in that case, hysteresis loss are inversely proportional to frequency, and eddy current losses will not be will not change. You just simply substitute here V by F whole square. F square gets cancelled. Voltage is constant, so eddy current loss are going to be constant. In the same way, if you reduce the voltage and keeping the frequency as constant, K means constant, the flux density is not going to be constant, and hence your decurrent hysteresis losses will be like this. These four cases are very, very important. Most of the times the questions will be asked on this case or otherwise this case, because you can get a chance of 2 marks question. The question looks like very lengthy, but if you can understand the data, then you can easily answer it. The only thing is you need to check whether the voltage to frequency ratio is constant or not, and in which case it falls. So simply, otherwise, if you don't remember, you check it whether the voltage to frequency ratio is constant. If it is constant, just make the B maximum, eliminate B maximum and write hysteresis loss proportional to frequency, and eddy current loss is proportional to frequency square. If it is not constant, then you consider them. Whatever the term which is constant, do not consider it, and remaining other terms you can consider it. Okay, I have a simple question which is asked in GATE examination. You see here. The single phase transformer has a single phase transformer, single phase two winding transformer. The supply frequency and voltage both are increased by 10%. The percentage changes in the hysteresis loss and eddy current losses is asking. So we need to check whether the voltage to frequency ratio is going to be constant or not. So V2 is how much? Maybe V1, let us take up how much is V1. Let us take up it as a rated voltage. And F1 is rated frequency. Okay. We do not know, he did not mention. So V2 is how much? He's saying that 10% increased. That means what? Compared to what? Compared to rated voltage. So 1.1 times rated voltage. Frequency is also 10% increased. So 1.1 times rated frequency. Now, so here 1.1 is cancelled. So the flux density in the second case and the flux density in the first case, both are same. So I can write hysteresis loss proportional to frequency and eddy current loss is proportional to frequency square. As the frequency is increasing, definitely hysteresis loss will increase. As the frequency increases, definitely hysteresis eddy current loss also increases. There is no question of getting negative value. There is no question of getting negative value. Negative means decreases, because he's asking percentage change now. So definitely it won't be decreases, it will definitely increase. Now here, if I take up WH2 divided by WH1 is equals to F2 is how much? 1.1 times F1 divided by F1. So if I can cancel out the WH2 hysteresis loss in the second time, in the second case, it will be 1.1 times the hysteresis losses in the first case. That means what? 10% more than the first case. Similarly, if you do here, it will be 1.1 times whole square. F1 by F1 can be cancelled into WA1. So it will be 1.2 times WA1, which means 21% greater or 21% more. Okay, so 21% more. So hysteresis losses will be 10% and eddy current losses will be 21%. So hence the option is A. Okay, I hope it is clear. Now coming to the other test, that is short circuit test. So short circuit test, the equivalent circuit looks like this. And the total resistance referred to the primary side, total reactance referred to the primary side. Generally, we short the low voltage winding and we keep the voltage on high voltage side. This is not even rated voltage, which is generally, less than the rated voltage, hardly 8 to 10%. That is enough. So from this equivalent circuit, you can find out the equation short circuit voltage, the power factor. You can draw by the way, the triangle also, impedance triangle. So this will be R01 and this will be X01 and this will be Z01. So from that, you can calculate cos phi SC. And there is a short circuit current is nothing but rated current. So short circuit current is equal to VSC by Z01. So which is rated. If you want more than the rated current, we call this as steady short circuit current, which happens at rated voltage. At rated voltage. So when you apply rated voltage on the high voltage side, the current circulated in the winding is not rated current, it is more than the rated current, and that current is called as steady short circuit current, which is inversely proportional to per unit impedance. Okay. And the next problem, next topic is voltage regulation. Remember voltage regulation, the change in terminal voltage at the secondary terminals from no load to any load you can take up. So this X represents the percentage loading, and the formula is percentage R into cos phi 2 plus or minus percentage X into sin phi 2. So plus is for lagging power factor loads and minus is for leading power factor loads or capacitor loads. So generally, percentage R represents the full load copper losses. Okay. So you can take up in another manner also the voltage regulation formula. Here I to R02. Here percentage R can be taken as resistance drop with respect to base value. So I to R02 divided by E2, I to X02 divided by E2. So the same. This equation itself, it's rewritten like this. And here the points are the condition for maximum regulation, condition for minimum regulation you need to consider. So this is condition for minimum regulation. So if you want to get maximum regulation, the load power factor angle must be equals to internal impedance angle. This is internal or winding impedance angle. Okay. So XL by RL is equal to X02 divided by R02. This happens generally at lagging load. And minimum regulation, which is nothing but zero regulation, and happens at, um, it's to say exactly 90 plus theta 2 is equals to 5, phi 2, like that you'll be getting. But anyhow, the condition is load capacitive reactance load to capacitive reactance to the resistive nature is equals to R02 divided by X02, and this happens at leading power factor. This happens at leading power factor. Generally, this phi 2 is equals to 90 plus theta 2, probably. Okay. 90 plus theta 2. If you take up the, I'll show you the triangle. If you take up the triangle, it looks like this actually. This is R02, and this is X02, and this is Z02. This is the impedance triangle, so I can write it as theta 2. And this is RL, this is XC, and this is ZL. So this is load power factor triangle. So tan phi 2 can be taken as XC by RL. Tan phi 2 can be taken as XC by RL. Okay. So if you want to get the power factor here, like this, phi 2. So now cos phi 2 during minimum regulation will be adjacent side by hypotenuse. That is X02 divided by Z02. So we take up the condition as here, like this. Theta 2 plus phi 2 is equals to 90 simply. Theta 2 plus phi 2 is equals to 90. So this is the triangle for minimum regulation condition. Be careful. So the power factor at minimum regulation, be careful, X02 divided by Z02. The power factor at maximum regulation is R02 divided by Z02. So this is very, very important point you need to understand. Okay, because this comes out as not same as a maximum regulation condition. It comes out as opposite. XC by RL is equal to R by X. Remember that point. So if you look at the question, a 5 kVA 50 by 100 volts single phase transformer has a secondary terminal voltage of 95 volts when loaded. The regulation of the transformer is asking regulation. So we know the percentage regulation, what the percentage regulation is equals to percentage X into percentage R cos phi 2 plus R minus percentage X sin phi 2. Okay, we have the secondary terminal voltage. Okay, is directly asking regulation. So he did not mention anything about R and X, but regulation we can write E2 minus V2 divided by E2 into 100. So this regulation is asking. Okay. So anyhow, we know I can say that this is the primary and this is the secondary. Obviously, the secondary terminal voltage is 95. So I can say this is E2 and this is going to be V2. So secondary terminal voltage is V2 now. Okay. So you can do this. He did not mention anything about the power factor also. So simply the terminal voltage is given, and from the nameplate details, you can take up the induced EMF. So Nothing. So you can take up directly as 100 minus 95 divided by 100. So you'll get it as 5%. Such a simple question, which is asked for 1 mark in GATE. If they mention regulation, if they mention resistance and reactance, and then the power factor, so you just need to substitute here and you'll get it according to the load. So this is the percentage load. X is percentage load. So X equal to 1 when it is 100% load or full load, I can say. X equals to 0.5. That means what? Half of the full load. Okay, like that you can substitute. Yeah, the power factor at minimum regulation. This point I thought of saying, but anyhow it is missed and it came into the next slide. Apart from regulation, there is one more important topic, that is efficiency. So efficiency, we know that output divided by output plus losses. So here iron losses and copper losses. Here we will be taking the current as X times I2, because I2 I'm considering it as full load, and with respect to that current I'm taking the percentage loading also. So that is the reason why here X times I2 whole square you'll be getting. So that is X square times full load copper losses. Actually the full copper loss can be taken as what? Copper loss can be taken as I2 square into R02, right? So if it is changing with respect to load, so X times I2. That is what it is written as separately. X square times I2 square into R02 is written as full load copper losses. Now they'll ask you the question, condition for maximum efficiency. At what load you'll get maximum efficiency, at what point you'll get maximum efficiency. So when the copper losses changes and equals to iron losses, you'll get maximum efficiency. And the load during this maximum efficiency is the percentage loading is root of WI by full load copper losses. Be careful, this is full load copper losses. And at maximum efficiency, the total losses are going to be equals to 2 times iron losses, but not equals to 2 times copper losses. You cannot say 2 times copper losses. So the KVA corresponding to maximum efficiency is, once you get the percentage load corresponding to maximum efficiency, you just simply multiply with full load KVA. You'll get KVA corresponding to maximum efficiency. Okay. So I have a question here. Just look at the screen. A single phase transformer has a maximum efficiency of 90% at full load and unity power factor. Now the efficiency at half load at the same power factor is asking efficiency at half load. So X value is 0.5 and the power factor is going to be same power factor, means unity. So what is the formula? X into E2 into I2 into cos phi2. X value is 0.5 into E2 I2. We do not know any rating, so simply I'm writing it as in terms of kilowatts into power factor is unity divided by 0.5 into kilowatts. Or let me in simple manner, let me write it as just 1 into plus iron losses we do not know and copper losses we do not know. Here 0.5 square into full load copper losses. He's asking the efficiency. This one is asking this efficiency. If you want to calculate this efficiency, you need to substitute the iron losses value and full load copper losses value. But we know another data, that is the transformer has maximum efficiency of 90% at full load. So full load means X value is 1 into unity power factor divided by 1 into 1 into 1. So this is percentage loading. This is KVA rating. Just I've taken it as 1 per unit, and power factor. So plus iron losses plus full load copper losses. You can write like this. Actually, you can write these two losses as 2 times WI. Why? Because this is not simple efficiency. This is maximum efficiency. At maximum efficiency, total losses equals to 2 times iron losses now. Okay. So if you can solve it, then you'll get it as 2 into 0.9. Probably if you solve it and get it, probably 1 divided by 0.9 or 1. Maybe let me solve this one. If you cross multiply, it will be 0.9, 1.8. 1 minus 0.9 will be 0.1. 0.1 divided by 1.8. It comes out as 1 by 18 kilowatts. If you take up this as kilowatts, if you take up in per unit, no issues. So this is the iron loss, uh, at there is iron loss. Irrespective of the load, this loss is going to be constant. Right? Now, we know at maximum efficiency, the copper losses equals to iron losses. So copper losses, which load it is? Full load. So full load copper losses is equals to iron losses. And that is also 1 by 18 kilowatts. Now, if you substitute in this equation, you'll get it as 0.5 divided by 0.5 plus 1 by 18 plus, so it's 0.5 square is 1 by 4 into 1 by 18. So solve this, probably you'll get the answer. That's the efficiency of the transformer. I hope it is clear. So it's you need to find out the corresponding losses and then substitute, so that you'll get the answer. Now another topic is auto transformer. So they'll ask you the questions on induction kVA, conduction kVA, maybe 1 mark. Induction kVA will be 1 minus k times the full load kVA. Conduction kVA will be k times the full load kVA. Okay. Now, if the two winding transformer is reconfigured as auto transformer, okay. Actually, so far whatever the discussion we had, not two winding transformer. If it is reconfigured as auto transformer, then the new rating will be very, very high. New rating will be very, very high, and that rating they'll ask you. Okay. Series additive polarity, series subtractive polarity, they'll ask you. And sometimes they'll ask you the efficiency of auto transformer also. So the only thing which is not going to change is, if it is a two winding transformer, the current carrying capacity, voltage rating, they don't change. So if the voltage rating does not change, flux does not change. If the current does not change, then the copper loss also does not change this. So the iron losses and copper losses will be same as the two winding transformer. There is no change. The only thing is here rating will change. So you need to calculate that rating according to the configuration. Simply it's voltage into current. That's it. You need to calculate. And you can calculate the efficiency. There is another topic called parallel operation. So it's like same as like current division rule only. So this is the total load capacity. Okay. Let me rewrite this one. So this is a load kVA divided by, if this is, it's like opposite impedance divided by total impedance simply. So I2 is equals to entering current into opposite resistance divided by total resistance. The same way, current is similar to current division rule. Similar to current division rule. Okay. If they give you the Z in per unit value, please be careful. Convert the per unit impedance according to the base value. Convert the per unit impedance according to the common base value and then go ahead. Okay. So those are the important formulas from the transformer. And now if you see the induction machines, so induction machine can be operated in 3 modes, to say exactly 2 modes. One is going to be motoring mode, generating mode, and this is plugging or braking mode. In motoring mode, the slip value is definitely less than 1, of course greater than 0, so it is generally positive. In motoring mode, the rotor speed is always less than the synchronous speed, and hence the slip is always positive and the rotor speed is ns of 1 minus s. In generator mode, the rotor speed is greater than the synchronous speed, so slip is negative, so you'll get rotor speed as ns of 1 plus s. And in braking mode, we will reverse the phase sequence, or we will reverse the supply phase sequence. Therefore, rotating magnetic field of the stator will reverse, but still the rotor rotates in the forward direction, maybe in the clockwise direction. And that's the reason why we will be taking it as ns minus half minus nr. No problem, you can take up minus ns minus nr divided by minus ns, because whenever you reverse the phase sequence, the rotating magnetic field direction also changes. So still here also you'll get positive only. Minus, if you take up common, then minus minus can be cancelled. So you'll get ns plus nr by ns. So you'll get it as greater than 1. So slip greater than 1 will happen in braking condition. So I have 3 questions. So they are asked in different manner. I just clubbed them. Just look at the screen. A three-phase induction motor is wound for 4 poles and is supplied from a 50 hertz system. Okay. Now he's asking calculate the synchronous speed. So what is the synchronous speed? ns equals to 120 f by p. 120 into 50 divided by 4 poles. So you'll get 1500 rpm. The rotating magnetic field rotates at 1500. Now he's asking rotor speed. What is the rotor speed? The rotor speed is equals to nr is equals to ns of 1 minus s. The rotor speed at 4% slip. So 1500 of 1 minus 0.04, you'll get 1500 into 0.96. You'll get probably 1440 or something else, 1460. You'll get 0.96 into 1500. You'll get 1440 RPM. Similarly, the rotor frequency when the rotor runs at 600 RPM. Rotor frequency is slip times the supply frequency. Okay. What is a slip? Is he has given the slip value can be taken as ns minus nr divided by ns. We know the synchronous speed is 1500. Rotor speed is not, don't take the rotor speed as 1440. He has given the rotor speed as 600. So if you take up, you'll get it as 900 divided by 1500. So 9 by 15. So 9 by 15 times it is 50. So you'll get it as 9 into 50 divided by 15 comes out as around rotor frequency as 30 hertz. Okay. So probably you'll be getting 30 hertz. This is the rotor frequency. So this kind of simple questions can be asked in GATE for 1 mark on slip. There is one more topic, that is equivalent circuit. It is same as a transformer only, same as a transformer. Okay. But they'll ask sometimes exact equivalent circuit. So when they ask exact equivalent circuit, you need to calculate Thevenin's voltage and Thevenin's impedance and go ahead. Otherwise, simply R1, X1. This is approximate equivalent circuit. R2 dash, X2 dash. R2 dash will be R2 by K square. X2 dash will be X2 by K square. That's it. Okay. So they'll be asking you to calculate the electromagnetic torque at full load, at starting, at different load conditions. They'll ask. Okay. So you need to substitute. If they are asking full load current, you need to substitute. If they are asking full load torque, you need to substitute full load current and full load slip. If they're asking starting torque, you need to substitute starting current and starting slip, and so on. Okay. So this is what the conditions and the corresponding currents. How do you calculate these currents? How do you calculate these slips? From the these resistance values, reactance values, and once you know these values, simply voltage divided by this impedance, you'll get it, the current. Okay. So sometimes they'll ask you maximum mechanical power also. So the maximum mechanical power can be calculated like this. And if they ask torque, simply power divided by omega. Power divided by omega, if you do it, then you'll get the answer. Remember, the very important point is maximum torque will happen at what value of resistance, or if the maximum torque to be occurred at the time of starting. So at starting, the slip is 1. So this is what value of extra resistance you need to insert in the rotor resistance to get maximum torque at starting. So that kind of questions also they'll ask. Slip corresponding to maximum torque is R2 by X2. Okay. And there are some ratios also, torque ratios. Torque ratios. That is starting torque to maximum torque, full load torque to maximum torque. You just remember starting torque, starting slip is 1, maximum torque, so maximum slip. So simply 2 into 1 into Sn divided by 1 square plus Sm square. In some textbooks, they'll write it as A, slip corresponding to maximum torque as A, slip corresponding to full load torque as S. So full load torque to maximum torque. So full load slip, maximum torque, maximum slip, full load slip square plus maximum slip square. Maximum slip square. Okay. So these are the torque ratios. These are the torque ratios. Okay. So if you look at this question, a three-phase 24-pole 50-head star-connected induction motor has a slip ring rotor. The rotor resistance and reactance per phase are 0.03 and 0.5 ohms respectively. Neglect the stator impedance. The speed at maximum torque is asking speed. So we know the speed formula as NR is equals to NS of 1 minus S. Speed at maximum torque is asking. So if he is asking speed at maximum torque, you need to substitute slip at maximum torque. So what is the slip at maximum torque? You will get R2 divided by X2. Actually, the slip times the reactance will change and equals to resistance to get maximum torque. Okay. Right. So if you substitute resistance value 0.03 divided by reactance value 0.5, so you'll get the slip value. It comes out to be 0.03 divided by 0.5, it comes out to be 0.06. And if you substitute, as it is synchronous speed for 24 poles, so 120 into 50 divided by 24 poles into 1 minus 0.06. So it comes out as 0.94, right? 1 minus 0.06 will be 0.94. So 120 into 50, it comes out as 6,000. 6,000 divided by 24, 250. 250 into 0.94 comes out as around 235. Okay. All right. So we'll see one more question. That is, a three-phase squirrel cage induction motor has a starting torque of 150% and maximum torque of 300% with respect to rated torque, at rated voltage and rated frequency. Neglect the stator resistance and rotational losses. The value of slip for maximum torque is the value of slip for maximum torque. So SM is asked. We know the torque ratios, right? Starting torque to maximum torque, we know, and full load torque to maximum torque also, we know. So I can write it as 2 into 1 into slip corresponding to maximum torque divided by 1 square plus SM square. And this is 2 into SFL into SM divided by SFL square plus SM square. Right. So starting torque of 150% and the maximum torque of 300%. So he has given this one and this one with respect to the rated torque. So he's asking slip corresponding to maximum torque. Which one you will use? We will use this one, right? So starting torque is 150%. 150%. So 150 divided by maximum torque is 300%. So 300. You can take up it as 1.5 divided by 3 also. No issues. Is equals to 2 into SM divided by 1 square plus SM square. So if you solve it, I think 15 divided by 3 or 1.5 divided by 3 comes out as 0.5. So 0.5 into 1.5 plus 0.5 SM square minus 2 SM. So it's a quadratic equation. Solve it. You will get the root 1 and root 2. So select the slip which is less than 1. Select the slip which is less than 1. Okay. One looks like greater than 1 and the other looks like less than 1. So select the slip which is less than general. Okay. And a very important topic is the power flow. So power flow in induction machine. This is stator input or motor input power. And once you give the power to the motor, you'll have a stator losses, the stator iron losses and stator copper losses. And the next power will be transferred to the rotor through air gap. So rotor input power is also called as air gap power. And once the rotor receives the power will be wasted in the form of rotor copper losses. Rotor iron losses are going to be neglected because the rotor frequency is very, very negligible at high speeds. And after the rotor copper losses, the next available power is gross mechanical power. And after the gross mechanical power, you'll be losing some power in the friction and wind days, so that is called as mechanical losses. And the remaining power is called as output power or shaft power. So the question can be on the full machine, and the question can be on the only on rotor power flow. So rotor input power, rotor copper losses, rotor gross mechanical power is having a relation like 1 is to S is to 1 minus S. From the power flow, we'll get to know. And we have a question on this one. A 10 HP 4-pole 15 Hz 3-phase induction motor is operating at 1450 RPM on full load. The stator copper loss is 231 watts and the rotational loss is 343 watts. What is the efficiency of the motor? So if you want to check the efficiency of the motor, output power by input power, or otherwise output power by output plus losses. Okay. So if you look at the power flow, it will be motor input minus stator losses, and this will be rotor input minus rotor losses, and this is going to be gross mechanical power, and then you can call it as the mechanical losses, and we'll be having the shaft output power. So what are the losses he has given? He has given only stator copper losses. He did not mention anything about stator iron losses. So it doesn't matter if he has not mentioned. Take only stator copper losses. We have 231 watts. Do we have motor input? No. The rotational losses he has mentioned. The rotational losses he has mentioned it as 343 watts. Okay, fine. Now what is the efficiency of the motor? If you want to calculate efficiency of the motor, you need to calculate output power. By the way, he has given 10 HP. This is the output mechanical energy only. And by the way, the induction motor is operating at full load. So this is a full load output only, right? So 10 HP is nothing but 10 HP into 736 watts. So 73,600, what otherwise 73.6 kilowatts. Now for that, if you add 343, then you will get gross mechanical power. So 73,600 plus 343, you will get it as gross mechanical power. It will be shaft power plus mechanical power. Mechanical losses. I'm getting 73,943 watts. Okay. Once you know the gross mechanical power, you can calculate rotor input. There is a relation, right? There is a relation we have just seen. So gross mechanical power in terms of input can be taken as 1 minus S into rotor input. So we want rotor input. Rotor input is taken as gross mechanical power divided by 1 minus S. So rotor input is equals to gross mechanical power divided by 1 minus S. We know the gross mechanical power as 73,943. What is the slip? Now slip can be calculated from this rotor speed. So if the rotor speed is 1450, then the slip is equals to, for 4-pole 50 heads, the synchronous speed is 1500 minus 1450 divided by 1500. So it comes out as 50 divided by 1500. Probably comes out as 5 1s, 5 3s, 1 by 30. So if I substitute 1 by 30, we'll get rotor input. 1 by 30, 1 minus answer, and 73,943 divided by answer. I'm getting the rotor input as 76,492.75 watts. If the rotor input is this much, then you can add the stator losses. So if you add stator losses, so it's like rotor input plus stator losses. For that, if I add 231 stator losses, then I'm getting 76,723.75. So you'll get output as 73,600 divided by input as 76,723.75. So if I do it, I'll get it as around 95.92%. Maybe 95.92, I'm getting 95.6. Approximately C could be the answer. Okay. So this is how you can do the calculation in power flow. And there are starting methods of induction machine like the DOL starter, series reactor starter. DOL starter does not change any. Uh, DOL starter does not change any current here, and it does not control the current. Series reactor starter can control the current by based on the tapping. Okay. So therefore, the starting torque is also going to be changes by x square. The auto transformer also reduces the current by x times, and the starting torque also going to be changes by x square times. Remember, there is a small difference. The starting torque drawn by the motor is x times reduction, whereas the starting current drawn by the entire set, auto transformer plus motor, is x square times reduction. And the star delta connection will be like this. The star connection will draw the current uh, compared to the delta connection is 1/3 of delta connection, compared to delta connection. If you take up only star connection, it will be V by root 3, phase voltage by root 3 times the impedance. So you'll get it as 1 by root 3 whole square will be 1 by 3 you'll get. So this comes out as 1/3. Right. So remember the formulas, based on that you may get a question. And speed control, it's like constant torque loads, variable torque loads. We'll be getting the equation behind the speed control technique is this one. SE2 square divided by R2. So voltage control, rotor resistance control. Whatever may be the technique here, the torque produced in the second case and the first case needs to be same, because the loads are constant torque loads. So I can write S2 V2 square is equals to S1 V1 square. And apart from this, you can calculate slip 2. And once you calculate slip 2, you can calculate rotor resistance, rotor speed. Similarly, the rotor resistance control technique also, S2 divided by, here the voltage is maintained as constant in this case. So only we are changing resistance. So from this one, you can calculate slip 2. And once you calculate slip 2, you can calculate the rotor resistance, the rotor speed. Okay. And then next, if you look at the question, a 6-pole 50 hertz induction motor is operating with rotor resistance R2 equal to 0.2 ohms per phase and speed N equal to 950 rpm. Now the motor has to operate at a speed N2 equal to 800 rpm, then find the value of inserted resistance in the rotor when the load torque is constant. So when the load torque is constant here, I can write S2 divided by R2 plus RXV is equals to S1 divided by R. What is the slip in the first case? The slip in the first case, it will be, as it is 6-pole 50 hertz, the synchronous speed is equals to 120 into 50 divided by 6, you will get 1000 rpm. So the slip 1 is equals to 1000 minus 950 divided by 1000. And the slip 2 is equals to 1000 minus 800 divided by 1000. Okay. So 50 by 1000, you'll get it as 5 by 100, maybe 1 by 20. And 200 by 1000, it will be 2 by 10, but it will be 0.2. So it comes out as 0.05, and this is 0.2. So probably it looks like this. Okay. So if you substitute slip 1 as 0.05 and R2 value is 0.2 ohms per phase, slip 2 as 0.2 divided by 0.2 plus Rx1. So if you solve it, then you will get it as, let me solve this one. I'm getting it as the external resistance is around 0.6 ohms per phase. Okay. Now, similarly, there will be another method, that is rotor EMF injection method. So if you add the EMF, then induced EMF increases. So the torque equation is this one, ES into E2 square divided by R2. I'm keeping the resistance as constant. I'm increasing the EMF now. So S2 into E2 plus or minus EI whole square. If I add the EMF in the same direction, it will be addition. If I add the EMF in out of phase, it will be minus. So E2 plus or minus EI whole square is equal to S1 into E2 square. So there is a possibility to get super synchronous speed in phase induction and sub synchronous speed in out of phase induction. And the last one is V by F control technique, variable voltage, variable frequency control technique, by maintaining the rotating magnetic field as constant so that the starting torque, maximum torque, slip corresponding to maximum torque will look like this. And the torque, by the way, the torque is still the same. If you want to get the constant torque output, then the relative speeds must be same, but not per unit slips. Per unit slips can be different. Relative speeds must be same. If initial synchronous speed is 1500, initial rotor speed is 1400, then it will be 100 rpm. 100 rpm with respect to 1500, it's the per unit slip. And now after decreasing the frequency, the synchronous speed changes. Maybe let us take up it as 1000 minus 900 it has to be. Then only the relative speed is 100. So 100 divided by 1000, it is not equals to 100 divided by 1500. These two are not equal. Relative speeds will be same, but per unit slips are not going to be same. Per unit slips are not going to be same. Okay. So if you take up the question, the speed of a 4-pole induction motor is controlled by varying the supply frequency while maintaining the ratio of supply voltage to supply frequency, V by F ratio as constant. At rated frequency of 50 Hertz and rated voltage of 400 volts, its speed is 1440 RPM. Now find the speed at 30 Hertz. Now, to have a constant torque load, so the torque 1 and torque 2 will be same. So it's like NS2 minus NR2 is equals to NS1 minus NR1. What is NS1? The synchronous speed at 50 Hertz, it will be 50 Hertz 4-pole, it will be 1500, 120 into 50 divided by 4. Now, what is the rotor speed at 50 Hertz? At 400 volts, 50 Hertz, it is 1440. Okay. So the relative speed is 60 rpm. Now here the synchronous speed at 30 Hertz you need to calculate. The synchronous speed at 30 Hertz, it will be 120 into 30 divided by 4 poles. So 3600 divided by 4, you will get it as 900 rpm. So 900 minus NR2 is equals to 60. And the rotor speed will be now 900 minus 60, it comes out as 840 rpm. Okay. So this is how you can calculate the rotor speed for variable voltage and variable frequency control technique. Okay. Now this is one more very important point to check the stability operating point. So whenever the load torques and motor torques are given, what you need to do is you just need to take up the speed point and adjust the speed. If you adjust the speed, maybe increase or decrease, you decrease or increase, anything is okay. If I decrease the speed here, this is a motor torque and this is a load torque. So at this speed, motor torque is greater than load torque. If motor torque is greater than load torque, definitely the speed will accelerate. That means what? Even though you create a disturbance, again the speed will accelerate and attains the same speed. So this is a stable point. Stable point. Right, that is what you need to understand. Okay. Now coming to the another topic, that is DC machines. In DC machines, hardly will be having voltage and current equations, torque and EMF equations. So if you can remember these voltage equations for separately excited machine, shunt machine. If it is a motor, how will be the equation? If it is a generator, how will be the equation? So if it is a motor, it likes, supply voltage minus resistance drop is equal to back EMF. If it is a generator, E minus IARA is equals to terminal voltage. So that is what the equations are given. And accordingly, even for the series machines also, you can take up compound machine also, you can take up. The point you need to remember is E is equals to 5 PNZ by 60A. And from this equation only, we have got K5 omega. And from power is equal to torque into omega, if you substitute power in place of power, if you substitute EB into IA, then you get this torque equation, K5 omega. So these equations are very, very, very important in order to solve the questions. All right. And remember, for the shunt machines or separately excited machine, the flux is almost, most of the times it is going to be constant. So I can write E is equal to K into omega, P is equal to K into IA. Whereas for series machine, the flux is proportional to armature current. So I can write it as K times I square before saturation. But it is also equals to K times IA if the field winding is saturated. If the field winding is saturated, then you can take up K times IA. So most of the questions, 99.99% questions can be solved with these three equations. E is equal to K phi omega, T is equal to K phi omega, power is equals to torque into omega. You see here at 200 volts, 2000 RPM, 10 amperes separately excited DC motor has an armature resistance of 2 ohms. Rated DC voltage is applied to both armature and field windings of both of the motor. If the armature draws 5 amperes from the source, the torque developed by the motor is. He has given it as a separately excited motor. So draw the equivalent circuit. It's EB and this is a motor. By the way, it's 200 volts. When it is running at 2000 RPM and it draws 10 amperes, by the way, the armature resistance is 2 ohms. Okay. And it is operating at rated voltage on both the field and the armature. So the flux is constant. Now what is asking? He is not asking the torque developed at 10 amperes. He is asking the torque developed at when it is drawing 5 amperes. When it is drawing 5 amperes. So what is the electromagnetic torque developed by the motor? So if you want to calculate torque developed by the motor, we know the flux is going to be constant. So torque is equal to K phi Ia. So phi is constant. So K into Ia. So Ia, I know the 5 amperes. If you can calculate K, then you can calculate torque. How do you calculate K? So K can be calculated from the other equation, that is E is equals to K phi omega. So E, how do you calculate? Whenever it is drawing 10 amperes, there will be a drop of 20 volts. So E can be taken as 200 minus 20, that is 190. And omega is 2 pi n, that is 2000 by 60. So if you solve it, you'll get K. And substitute here the K value, maybe 1.7 or something else, and you'll get that some X, and X into 0.5, you'll get the torque, Newton meters. That's it. So it's all about K calculations. Many questions can be solved with these two equations. E is equal to K phi omega, T is equal to K phi Ia. Okay. And there will be question on speed control also. A 220 volts, 15 kilowatts DC shunt motor with an armature resistance of 0.25 ohms and a rated line current of 68 amperes at rated field current of 2.2 amperes. Okay. The change in field flux required to obtain a speed of 1600 RPM. Initially, the shunt motor is rotating at 1000 RPM. Okay. So let me give the 220 volt supply, and the armature resistance he did not mention, but he has mentioned it is taking a line current of 68 amperes and a field current of 2.2 amperes. Of course, armature resistance he has mentioned, that is 0.25. He did not mention the shunt field resistance. And it is running at 1000 RPM. Let me take up it as case 1, so N1. Now, he's asking what should be the change in the flux value. What should be the change in flux value so that the speed of the motor will increase to 1600 RPM. Okay. So this is back EMF 2 and this is back EMF 1. It is 220 volts. And it is going to draw a line current of 52.8 amperes and a field current of 1.8 amperes. Of course, by the way, this is 0.25 volts. You know the speed is directly proportional to back EMF and inversely proportional to flux. So there is a change in flux. N2 by N1 is equals to EB2 divided by EB1 into phi1 divided by phi2. Is asking the speed increment. If the speed is if you are expecting the increment in speed, the flux must be reduced. Now, what is asking? The change in field flux is asking. So the flux must reduce to get the increase, to get the speed increment. So we should not increase the change in flux should not be increased. So increase. This can be eliminated. A and C can be eliminated. Now I know N2 that is 1600, N1 I know that is 1000. Now EB2 you need to calculate, and EB1 you need to calculate. What is EB2? 52.8 amperes is entering and 1.8 is leaving. So remaining 51 amperes will flow like this. So it will be 220 minus EB2 is equals to 220 minus 51 into 0.25. You will get the answer. Similarly, EB1 also 68 is entering and 2.2 is leaving. So it will be 60, if it is 365, so 65.8 amperes. So EB1 is equals to 220 minus 65.8 into 0.25. So if you solve this, 65 into 0.25, 220 minus answer, I'm getting it as 203.55 volts. The other one is going to be 51 into 0.25 and 220 minus answer comes out as around 207.25. So if I substitute 207.25 divided by 203.55 into 51 by 52. So if you solve it, 51 by 52 you will get ratio, but that is not the ratio. We need 52 by 51. So that is the answer. Probably you will get decrement of 36.36%, probably. Okay. So this is how you can do the questions. And there is another topic called armature reaction. Based on the armature reaction, you can calculate demagnetizing ampere turns per pole, cross magnetizing ampere turns per pole. So demagnetizing ampere turns will be 2 theta divided by 180. And if you subtract from total ampere turns, the armature reaction ampere turns is Z into IA divided by 280. So from this one, if you substitute 2 theta by 180, then you will get cross magnetizing ampere turns. They'll ask you sometimes compensating winding ampere turns also. So compensating winding is placed in the pole shoe. So pole shoe is not going to cover the whole pole pitch. It is going to cover only just 70%. No? So pole arc by pole pitch is just 70%. So 0.7 times ZIA by 2AP. This is 2AP. So be careful here. Theta is theta electrical angle. So sometimes they'll give you mechanical angle. You can convert into theta electrical and substitute. Sometimes they'll give in commutator segments. So in terms of segments, commutator segments. So commutators of circular shape. So 360 angle divided by number of segments. So you'll get the angle for each and every segment. So once you get mechanical angle, you can convert into electrical angle and you can substitute in the formulas, you'll get it. And the next one is synchronous machines. Here. So the questions can be on pitch factor, can be on distribution factor. So the pitch factor to eliminate nth harmonic is cos n alpha by 2. And alpha is equals to, alpha is a short pitched angle, and it can be written as 180 by n. And the distribution factor to eliminate nth harmonic is sin m n gamma by 2 by m sin n gamma by 2. So n is the harmonic component, where n is nothing but harmonic component. Okay, so m is the phase belt and gamma is a slot angle. So phase belt slots per pole per phase and gamma is 180 by s by p. Okay, now m gamma, you'll get it as 180 by number of phases. This is what we call it as phase spread. Now, once you get all these KD, KP, then you can substitute in the EMF equations and you can solve per phase EMF equation. So be careful. Sometimes they'll ask you per phase EMF equation. Sometimes they'll ask you line to line value. And look at the connection, whether it is delta connection or star connection, and go ahead with that one. If it is two-phase connection, root 2 times phase value. If it is star connection, root 3 times of phase value. If it is delta connection, simply line value equal to phase value. So here the question is three-phase alternator with slots per pole per phase equals to 5, and the coil span is given as 12 slot pitches. Then the coil span factor is asking. Coil span factor is nothing but pitch factor. Okay. So we have seen the pitch factor formula, that is Kp is equals to cos alpha by 2. So if you want to calculate alpha, you need to find, uh, first of all, full pitched slots. So the full pitched slots can be taken from slots per pole only. He has given phase belt, that is M is equals to slots per pole per phase, and he said it is 5. So slots per pole is equals to 5. And this is a three-phase alternator. So 5 into 3, if you cross multiply 5 into 3, you'll get it as 15. So 15 slots, the winding has to be wounded for 15 slots. But he said that, uh, just a minute. But he said that the winding is wounded for 12 slot pitches. So if the winding is wounded for 12 slot pitches, then I can say that the alpha is equals to 15 minus 12. You'll be getting 3 slots. The winding is shorted by 3 slots. The winding is shorted by 3 slots. Yes, sir. So, but I want angle. So if you want to find out angle, so you have to calculate gamma, that is slot angle 180 by S by P. So you'll be getting it as 180 divided by S by P. You'll get it as around 12 degrees. Now for 3 slots, it will be 3 into 12. You'll get it as 36 degrees electrical. So that the pitch factor, the coil span factor is equals to cos 36 by 2 cos 18. Probably you'll be getting it as 0.951. So this could be the answer. Now moving on to the next question, that is, here the question is about a 6-pole alternator with 36 slots, carries 2-phase distributed winding. Each coil is short pitched by 1 slot, and a winding factor is asking. So winding factor is nothing but pitch factor into distribution factor. Okay. So if you want to calculate pitch factor, you need to calculate alpha. So if you want to calculate alpha, you need to calculate gamma. So gamma is equals to 180 by S by P. So 180 by number of slots are 36, number of poles are 6. So you'll get it as 30 degrees. How many slots? The winding is short pitched by just 1 slot. So alpha is equals to 1 into 30. You'll get 30 degrees. So Kp will be cos 30 by 2. It comes out as cos 15. Okay. So that is the pitch factor. And if you want to calculate distribution factor, Kd, you have to calculate sine m gamma by 2 by m sine gamma by 2. So here you need to calculate slots per pole per phase. That is phase belt, slots per pole per phase. So we got slots per pole as 36 by 6. That is, 6. And number of phases are 2 phase. So you'll be getting it as 3. And gamma we have already calculated, that is 30. So that your Kd will be, distribution factor will be sine 3 into 30 divided by 2 divided by 3 into sine 30 by 2. So it comes out as sine 90 by 2 is sine 45. Sine 45 divided by and sine 15. Sine 45 will be 1 by root 2. So 1 by 3 root 2 into sine 15. So we have got Kp and value, Kp value and Kd value. You just take up now the winding factor. So the winding factor is equals to cos 15 into 1 by 3 root 2 into sine 15. So you'll get it as 1 by 3 root 2 into cot 15. Okay. So cot 15 by 3 root 2. This could be the answer. Okay. Now coming to the another topic, that is armature reaction for various power factors in synchronous generators and synchronous motors. It's for 1 mark they might ask. For lagging load, it will be demagnetizing effect of armature reaction. For leading load, it will be magnetizing effect of armature reaction. Whereas for unity power factor, it will be cross magnetizing. And when it comes to synchronous motor, for lagging load, it will be magnetizing effect. And for leading load, what I can say, leading power factor, lagging power factor, magnetizing effect, and leading power factor, it will be demagnetizing effect of armature reaction. Whereas unity power factor, it will be cross-magnetizing, whether it is generator or motor. The voltage regulation can be calculated as, change in terminal voltage from no load to full load with respect to full load. You can call it as, full load voltage regulation. If you take up half load voltage, then it will be half load voltage regulation. Now, this voltage can be calculated from the terminal nameplate details. Okay. And E can be calculated from this equation. So in the generator, the supply in the generator, generated EMF is equal to terminal voltage plus drop. So this drop, while calculating drop, be careful. This armature current may be leading with respect to voltage, may be lagging with respect to voltage. Plus is for leading and minus is for lagging. And theta is the internal impedance angle of the generator. So if not this way, you can calculate this way also. So E square is equal to V cos phi plus IARA whole square plus V sin phi plus or minus IAXS whole square. So plus is for lagging and minus is for leading. The same EMF equation, you can do it for even synchronous motor also. For the motor, we will give supply. So supply minus drop is equal to EMF. Here, the current direction gets reversed. So same formula, the current direction gets reversed here. So therefore, instead of plus or minus IAXS, you will get minus plus IAXS. Right. So here minus is for lagging and plus is for leading. Now, if you want to calculate the EMF, you need to calculate the synchronous reactance. So sometimes they don't give you synchronous reactance directly. They'll give you synchronous impedance. So synchronous impedance can be taken from open circuit characteristics, voltage, and short circuit characteristics, current. Okay. That rated field, rated current when the excitation is given to you. Sometimes they'll ask you saturated synchronous impedance. If they ask you saturated synchronous impedance, you need to take up the field current higher value, the highest value. So open circuit voltage for certain field current they'll give you. Short circuit current for certain field current they'll give you. Out of these two, which current is higher, you select that current. So that leads to saturation point, and you will get the saturation synchronous impedance. So once you get the synchronous impedance, ZS square minus RA square under root, if you do it, then you'll get synchronous reactance. Okay. So let me show you one example here. A single phase alternator has a synchronous reactance of 2 ohms and negligible armature resistance. So if I have a synchronous reactance of 2 ohms and negligible armature reactance, if it supplies 10 amperes to a pure capacitive load, at a terminal voltage of 200 volts, then the generated EMF will be, EG will be dash volts, and the regulation will be dash. So if you want to calculate generated EMF, just now we have seen the generated EMF is equals to E square is equals to V cos phi plus IARA whole square plus V sin phi plus or minus IAXS whole square. As it is leading load, so I'll be taking minus sign, minus IAXS whole square. So we know it's a pure capacitive load, so the power factor is going to be 0 leading. So if the power factor is 0, the sign component is 1. And we know resistance is 0. So if resistance is 0, this component is 0. So totally this component is 0. And we left out with E square is equal to V, that is 200 into 1 minus IA is 10 into synchronous reactance is 2 square. So square gets cancelled. So 200 minus 20, it comes out as 180. So the generated EMF is 180 volts, and the percentage regulation will be E minus V, that is 180 minus 200 divided by 200 into 100. So definitely, if the power factor is less than or equal to 0.8 leading power factor, the regulation will be definitely negative. Regulation will be definitely negative. You solve this one, you will get to know the regulation. Okay. All right. The another topic is important topic is power flow in the synchronous generator. They'll ask you to calculate active power flow and reactive power flow. Sometimes they consider armature resistance, sometimes they do not consider armature resistance. If they consider armature resistance, then the formula will be like this: EV by ZS into cos of theta minus delta minus V square by ZS into cos theta. If you want to calculate reactive power, in place of cos, you'll be having sine. That's it, nothing difference. If you differentiate the active power with respect to variable load angle, that power is called as synchronizing power. And synchronizing power divided by synchronous speed, you'll get it as synchronizing torque. If the armature resistance is 0, then the synchronous impedance is equals to synchronous reactance, and theta is equals to 90, because you can replace only reactance nature now, so you'll get 90 degrees. So if you replace it, then the active power will be converted as EV by X into sine delta, and reactive power will be looking like this: V by X into E cos delta minus V. Remember, E cos delta greater than V. So induced EMF is greater. So over excitation. Induced EMF is lesser under excitation. And the power factor also, please try to remember. Over excited synchronous generator operates at lagging power factor. So if E cos delta is greater, then it definitely Q is positive. Q is positive, no doubt it will deliver. It will deliver. Okay, it will deliver the reactive power. So let's have a look at this question. A synchronous generator is connected to infinite bus with an excitation EMF of 1.3 per unit. The generator has a synchronous reactance of 1.1 per unit, and it delivers a real power of 0.6 per unit to the bus. The bus voltage is 1 per unit. And he's saying that the resistance is neglected, the reactive power is asking. So we know the reactive power is equals to V by X into E cos delta minus V. V we know, X is also we know, E cos E also we know, that delta we do not know. That's it. So if you can solve delta, then you can calculate Q. So how to solve delta? We know active power equation EV by X into sine delta. Of course, this is also synchronous reactance. 1.3 into 1 divided by 1.1 into sine delta. What is the active power? We have got it as 0.6. So if you solve it, you'll get delta value some X and substitute the X value, you'll get the Q in per unit. Okay. So this is also asked in previous gate examination. Now, similarly, the power flow in synchronous motors also, right? So if armature resistance is negligible, then active power drawn by the synchronous motor, reactive power drawn by the synchronous motor will be like this. There is a small change in reactive power. In generator, it is E cos delta minus V. In motor, it will be V minus E cos delta. So that's a difference you need to understand. And if you see the phasor diagrams of synchronous generator, remember in the generator, E leads V. E leads V. In any case, whether it is any power factor, E leads V. Okay. So it's like as it is a generator, the terminal voltage plus drop is equals to induced EMF. So if you see here, terminal voltage plus drop is equals to induced EMF. Here also terminal voltage plus drop is equal to induced EMF. Terminal voltage plus drop is equal to induced EMF. Right. So that is how you have to draw, and from that one you can check up. Okay. You can check up this whether it is lagging. Okay, whether it is unity or leading, you have to see. And no doubt here you see E cos delta, the height is going to be E cos delta is going to be less than V. So if E cos delta is less than V, Q is positive, it delivers the reactive power. Okay. Psi is the angle between internal voltage and current. Delta is the angle between voltage and terminal voltage and generated EMF. Phi anyhow, phi is the angle between terminal voltage and the current, armature current. So please see the psi also, how it changes. Here phi is 0. Here phi is 0. The power factor angle is 0. Yeah. Okay. So for unity power factor, for leading power factor, sometimes they'll ask you based on the phasor diagram also. Be careful. Similarly, for motor, it's reverse. The V leads E now. V leads E. For motor, supply voltage minus drop is equals to EMF. Supply voltage minus drop is equal to EMF. Supply voltage minus drop. You see the phasor is quite opposite, is equal to EMF. Okay. Now in the same here also, if E cos delta, this height is E cos delta. E cos delta is less than V. If E cos delta is less than V, Q is positive. So Q is positive means absorption. An under-excited synchronous motor operates at lagging power factor and absorbs the reactive power. And you see the psi delta minus phi. An over-excited synchronous motor operates at leading power factor and delivers a reactive power and the psi is like this. Okay. So they'll ask you the questions on phasor diagrams also. Be careful. How will be the phasor diagram? You have to see. In this case, E cos delta, in this case, E cos delta is greater than V. Okay. This is V now. So E cos delta is greater than V. Here, E cos delta equal to V. So same way, you need to remember for generator also. Okay. Right. Now, if you see, a three-phase 50 Hz star-connected cylindrical rotor synchronous machine is running as a motor. The machine is operated from 6.6 kV grid. So if I take up the per phase voltage, 6.6 kV divided by √3, and draws a unity power factor, and draws a current at unity power factor. And of course, it has a synchronous reactance of 30 ohms per phase. The load angle is going to be 30 degrees, of course, minus 30 degrees. Now it's asking what is the power delivered to the motor. So if the synchronous reactance is considered and armature resistance is negligible, the power is taken as EV by XS into sine delta. He's asking power delivered to the motor. So he don't mention whether it is a three-phase power or single-phase power. So you need to understand it is a three-phase power. So now here 3 into E. What is E? We do not know. So how do you calculate? E square is equals to V cos phi. As it is a motor, minus IA RA whole square plus V sine phi minus IA XS whole square. So here it is, by the way, he said it is a unity power factor. So here power factor is 1 and sine component is 0. Resistance is 0. So here V is known, 66.6 kV by √3. And anyhow, this term is 0. But we know synchronous reactance, but we do not know armature current. So if you don't know armature current, you cannot calculate E. Now, what is other way? What is other way? How to calculate? So to calculate this kind of questions, you need to check the phasor diagram. So current is in phase with the voltage because the power factor is unity. So V minus IAXS, is equal to E. So the angle between these two is delta. So here I can say E cos delta is equals to V. Now from this one, I can calculate E. So I can calculate E as V by cos delta. So now you can substitute here. So the power delivered to the motor is E is how much? 6.6 K by √3 divided by cos delta. Cos delta is cos 30 into V is how much? 6.6 K divided by √3 and divided by XS, that is 30 into sine delta into sine 30. So if you solve it, you'll get the answer. And whatever the answer you get, that you just convert it to kilowatts because he's asking in kilowatts. Okay. Now, so far we have seen the formulas based on salient pole, based on cylindrical pole synchronous machine. Now, the formula with respect to salient pole synchronous machine differs because the reactances are different. There will be direct axis reactance, quadrature axis reactance, and therefore the induced EMF equation will be like this. So the blue ink is for generator and is red ink is for motor, synchronous motor. For synchronous motor, it will be V cos delta minus IQRA minus plus IDXT. And similarly, the standard formula also. Whereas the current equations will be same for motor or generator, doesn't matter. And coming to XD and XQ, if you want to find out XD and XQ, you have to do the slip test. And from the slip test, you'll get to know V maximum divided by I minimum will be XD and V minimum divided by I maximum will be XQ. Right. And there is the other question here. A salient pole synchronous machine, the developed reluctance torque attains maximum value when the load angle in electrical degrees is. So the salient pole, the total power developed by salient pole synchronous machine will be like this. It will be EV by XD into sine delta plus V square by 2 into 1 by XQ minus 1 by XD into sine 2 delta. So the first term is the power due to excitation. And the second term is the power due to reluctance. Is asking the developed reluctance torque attains maximum value. When will you get maximum reluctance torque? So if you want to get torque, the reluctance power divided by synchronous speed. I have reluctance power. So the reluctance power, if you want to get maximum, you'll get maximum reluctance power. You'll get maximum reluctance power when delta is 45. This will be maximum. When delta is 90, the excitation power will be maximum. And the total power will be maximum when the delta is less than 90 and greater than 45. In generally, delta will be around 60 to 70 degrees. If 60 to 70 degrees, then the total power developed by the reluctance machine or salient pole synchronous machine will be maximum. Similarly, torque also, power divided by omega, power divided by synchronous speed. If you do it, you will get it. Okay. So when will you get maximum value? Delta equal to 45. Okay. Right. Sometimes I'll ask you, if the excitation is lost, what is the power developed by the salient pole synchronous machine? If the excitation is lost, then then only reluctance power will be there. Okay. Now the next one is parallel operation. So here they'll ask you what is the power delivered by generator 1 or reactive power delivered by generator 2. For this, simply you go ahead with the power balance equation. Generation equal to demand. Okay, you just equate load powers and generator active powers and load active powers. Similarly, generator reactive powers and load reactive powers. So once you know this active powers and reactive powers, you can represent easily the power factor. So power factor cos phi is equals to P by S, or otherwise tan phi. If you want to calculate phi, then tan phi is equals to Q by P. So from this, phi is equals to tan inverse of Q by P. Now substitute here, you'll get the power factor. And there is one more other model that is based on the drooping characteristics. They'll give you the drooping characteristics from no load to full load. So you take up the drooping characteristics from no load. No load is a common point. Now here, one generator is having 3% drooping characteristics, other generator is having 4% drooping characteristics. Remember that do not ever select this operating point in this point, because 4% drooping characteristic generator can deliver the power, but not 3% generator cannot deliver the power. So do not select the operating point here, select the operating point in between. So this is the operating point we have selected. And use similar triangles method or slope method, you'll get the answer. Sometimes full load points given as same and no load points they'll give you as different. So they'll mention, they don't give you the graph, they'll mention only regulation constants. From no load to full load or full load, at full load they are operating like that, they'll mention. So please be careful. If the full load points are equal, if they said, if the generators are operating at full load points and at rated values, then take up the full load points are equal. Okay. And then proceed. Okay. Again, I'm saying do not select the common operating point in this zone. It's a non-operating zone. It's a non-operating zone. Okay. So that is all about the synchronous machines and all about the machines. Quick revision, including formulas and some examples. I hope it is clear. Thank you. Thank you so much. Have a nice day.